Let's look at some examples for sequences. We've already seen this one. This limit is 1. Is this convergent or divergent? Now let's see. What is the limit as n goes to infinity of n over root 10 plus n? One of the results above said that if I have this function and that for the natural numbers f of n equals a n, then this limit equals the limit as x goes to infinity of x over root 10 plus x, which means I can apply all of my limit rules that I have learned in order to evaluate these limits, right? So in this example, say I divide by root x, then I have root x over 1 plus 10 over x. Now, as x goes to infinity, this goes to 0, but this goes to infinity, so this whole thing goes to infinity, which means it diverges. Log n over n, again, we can look at the limit x going to infinity log x over x. Now this is infinity over infinity, which means I can apply the L'Hopital rule, which gives me x going to infinity 1 over x over 1, which is 1 over x, which is 0. This implies that the sequence converges. Is this convergent or divergent? Now if you look at the terms of the sequence, it's negative 1, 1, negative 1, 1, negative 1, 1. So we would say that the limit does not exist, or it diverges, because if you plot this function, it oscillates between 1 and negative 1 without really getting anywhere. What about this limit? So we have it oscillating, but we are also dividing by n. So this looks like negative 1, 2 over n, negative 3, sorry, it looks like um, negative 1, 1 over 2, negative 1 third, 1 fourth, negative 1 fifth, 1 sixth, so on. The first approach is to plot it, and you will see that although it oscillates, what is happening to it is it's getting smaller as it oscillates, so you expect it to go to 0. What we'll do is instead we're going to look at the limit of the absolute value, which is going to be limit n goes to infinity 1 over n, which is 0. So this converges. And remember that if the absolute value converges, then the actual one also converges. Right? So it converges and the limit is 0. Some more examples. If limit of a sequence is L and the function f is continuous at L, then the limit of the function of the sequence is the value of the function at the limit point. So here, this would just be sine of 0, which is 0. Okay, here's an important example. Discuss the convergence of n factorial over n to the power n, where n factorial is 1 times 2 times 3 times 4. So let's see. It looks like 1 factorial over 1 to the 1, 2 factorial, which is 2 times 1, 2 squared, 3 factorial, 3 cubed, 4 factorial, 4 to the 4. And let's expand these. This is 2 times 1 over 2 times 2. It's 3 times 2 times 1 over 3 times 3 times 3. 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. So what you notice is these cancel out to be 1. This is less than 1. That's 1. And this is necessarily less than 1. That's 1. All of these are less than 1. And it's getting smaller. Yeah, which means we can say that as limit n goes to infinity an, this is going to be 0. Now this is an analysis method because you cannot really use L'Hopital's rule because n factorial is not a continuous function even when you change it to x, and it's not even defined for real numbers. For what values of R is the sequence r to the power n conversion? Remember, this is a geometric series which we're going to look at later. But in general, if you think about it, when does this converge or not? Well, if r is more than 1, then it definitely diverges because it becomes infinite. If r is between 0 and 1, it converges. And if r is 1, also it converges because then the limit is infinity when r equals 1. And this is 1 or 0 depending on which one. If it's between 0 and 1, it's 0. If it's 1, it is 1. So it converges. Again, an important result to remember. Some definitions. A sequence is called increasing if the terms are increasing. It's called decreasing if the terms are decreasing. A sequence is called bounded above if there is a number m such that everything is less than m. And it's bounded below if everything is more than small m. If it is bounded both above and below, then we say it's a bounded sequence. That we have a theorem: every bounded monotonic sequence is convergent. What this says is there is a number m, and no matter how much you increase, an is always less than m. And it's also monotonic, means it's increasing. So what's going to happen is eventually, if you keep on increasing, you cannot really go beyond m, which means you have to be convergent because you have to stop somewhere, which implies that your limit exists because it is finite. So if you have a bounded monotonic sequence, then it is convergent. Show that this is decreasing. One way is to plug in the values. You have 1/2, 3/7, 3/8, and so on. You can claim that the denominator is increasing and the numerator is constant, so it is decreasing. Same thing here. You can say that the denominator is increasing faster than the numerator, so the an, the sequence itself, is decreasing. Investigate this recurrence relation. Okay, let's see what's going on here. A1 is 2, so A2 is 1/2 of 2 plus 6, which is 8 over 2, which is 4. A3 is 1/2 of 4 plus 6, which is 10 over 2, which is 5. A4 is 1/2 of 5 plus 6, which is 11 over 2, which is 5.5. A5 is 1/2 of 5.5 plus 6, which is 11.5 over 2, which is 5.75. A6 is 1/2 of 5.75 plus 6. So you see what's going on here is that this number is, what's that going to be? 5.75 plus 375, so 5.8 something something. So it's increasing, and it looks like it's gonna settle like that. Looks like it's gonna settle at 6. But what's the way to prove that? So let's see. What we have here is this recurrence relation. We're going to use a trick that we've used before in some bonus problems. We're going to say that the limit n goes to infinity, let this equal L. Then the limit n goes to infinity of a n plus 1 is also L. Because what we're saying is that the sequence cannot exceed L. That's where it goes when n goes to infinity. So it doesn't matter what the index is, which means limit n goes to infinity an plus 1 equals 1 half limit n goes to infinity an plus 6. Basically telling me that L is 1 half of L plus 6, or 2L minus L equals 6 and L equals 6. So this is a pretty common method for working out recurrence relationships to find the limit of the sequence.